Look at our shores, one of the Philippines' greatest treasures. Coastal communities depend on it mainly for livelihood. Yet, with every tide, new trash resurfaces, creating an endless cycle of cleanup that relies heavily on manual labor. Now, imagine if we had a tool that could clean them automatically. What if a robot could support and strengthen our community's efforts? Today, we, the Cleanest team, present a solution born from innovation, a tool that can help restore, protect, and sustain our shores for the generations after us. You see, tons of trash are being thrown into the ocean every day. As a result, this trash remains in the water and goes to different places brought by the waves. One example is at Barangay Aplaya in Bawan, Batangas, where numerous trash are being washed into their shoreline, coming from neighboring areas, especially during storms. People of this community make efforts in cleaning the area. However, one challenge is the difficulty of cleaning the waste that's been buried in the sand. This leaves us with the question of what if there could be a solution to efficiently solve this problem?
We present to you CleanEase, a smart shoreline cleaning robot that provides an automated, low labor solution to shoreline waste. CleanEase is designed to navigate along the shoreline, detect debris, and collect both surface level and partially buried trash. By integrating sensors and a collection mechanism, our robot reduces manual effort while improving the thoroughness of each cleanup. Though there are already existing innovations like CleanEase. What makes it different is the combination of automation, real-life monitoring, and an improved wheels and collection mechanism designed specifically for sandy terrain. This blend of navigation, detection, and collection gives CleanEase an advantage over manual cleanup, making it a practical solution for communities affected by storm-driven waste. And its features are autonomous navigation with GPS and sensors for self-driving shoreline cleanup, a real-time monitoring with cameras and sensor data accessible via app. It is also solar-powered, renewable charging for longer, low-cost operation, smart debris collection, ejector plate mechanism and sand sifter, and lastly, large storage bin with high capacity and easy to empty.
Let us walk you through how our robot actually works with our low fidelity prototype. So first, imagine the robot moving along the shoreline with its tracks, similar to the ones found in construction vehicles. As it drives forward, its sensors and cameras continuously scan the sand to detect visible trash and even some partially buried waste on the surface. Once the robot identifies debris, it will automatically position itself so the angled sieve can scoop it up. Now here's where the mechanism gets interesting. Equipped with an angled sieve behind it, the robot scoops up debris and repeatedly shakes it in a sifting motion, allowing sand to fall through while retaining the larger materials. The trash stays inside and is directed towards the waste hopper at the back, where everything the robot collects is stored. Inside the hopper, an actuator with an ejector plate is installed. This plate remains flush against the front wall of the waste hopper while the robot is still collecting. Although the trash collection process is automated, the robot still requires an operator. When the hopper is full, a signal alerts the operator. The rear wall lifts, and the actuator, which is activated by a foot pedal located behind the robot, pushes the ejector plate forward, clearing all of the trash without manual scooping. All components, the drive motors, the sensors, the sifter, and actuator, are powered by the battery, which is supplemented by a solar panel to extend its operating time. The robot's microcontroller coordinates all functions. This includes detecting trash, moving the wheels, operating the sifter, and controlling the ejector plate. In short, the robot moves, detects, collects, stores, and unloads all in its own with just a little responsibility needed from a human. And although our prototype is digital for now, the mechanisms and system flow are designed to function in a real world shoreline environment.
So for our financials and metrics, we kept everything simple and realistic since we are still in the simulation stage. Right now, the estimated cost of building CleanEase mainly comes from the basic materials like the sensors, motors, batteries, and frame. Maintenance is also very minimal because it mostly involves recharging and replacing small parts with when needed. For the metrics, we gathered realistic targets based on what similar small robots can achieve. CleanEase is expected to collect around 1 to 2 kilos of trash per hour, detect about 60 to 70% of buried debris, and cover around 100 to 200 meters in one run, which already reduces a big chunk of manual work, around 40 to 60% less labor needed. And as we continue improving the design, we expect costs to go down and the robot to become more efficient, especially once we refine the sensors and collection mechanism. Now and then, what? So at this stage, we have validated the problem through interviews with the community, and we now have a clear concept of our robot. We have created detailed sketches that show how CleanEase will move, detect trash, and scoop out both surface and buried waste. Our next step is to turn this sketch concept into a working prototype. To make that happen, we will need materials, technical guidance, and a space where we can test the robot in conditions similar to a shoreline. Basically, we are ready to move from ideas and sketches into actual building so we can finally see how Clinis performs in real world conditions.
For the beneficiaries, CleanEase creates impact on several levels. First, it directly helps our coastal communities. These are the people who struggle every day with waste washing onto their shorelines. With CleanEase, cleaning becomes easier, faster, and less tiring. And this matters most during rainy season when trash builds up the fastest and overwhelms local efforts. Second, cleanest benefits our marine ecosystem by removing trash before it breaks down into microplastics or get buried deeper. We protect marine life and prevent long-term environmental damage. Every piece of waste removed is one less threat to biodiversity. Third, local government units and environmental organizations also benefit. Cleanis supports their regular cleanup operations, giving them a practical tool to maintain cleaner coastlines. Instead of relying only on manpower and seasonal drives, they now have technology that strengthens their program. And overall, our project supports four major sustainable development goals. It aligns with SDG 9, industry, innovation, and infrastructure, because Cleanest is an innovative engineering solution to a community problem. With SDG 12 as well, by promoting proper waste management and reducing environmental impact. SDG 14, by protecting marine habitats from accumulated trash, and SDG 17, since collaboration with communities, LGUs, and environmental groups is essential in testing and implementing CleanEase. As we reach the end of our presentation, we just want to leave you with one thought. Our shorelines matter. They're part of our everyday lives. A place where families gather, where fishermen work, where tourists explore, and where our communities connect with nature. Clinius may be a prototype today, but it represents something bigger. It represents possibility. Every mechanism and every decision behind this robot was built with one question in mind. How can we help our coastal communities in a smarter, more sustainable way? So today, we're not just showing you a prototype, we're sharing a vision. Thank you very much for listening. With your guidance and feedback, this simulation can evolve into a real life working machine.